Chapter 2, Gaussian Elimination. So this is named after Johann Carl Friedrich Gauss, a German mathematician who lived in the 18th century and the 19th century. We consider a linear system in matrix vector format for a given system matrix A and given right-hand side vector B. So the matrix vector format is AX equals B, and the goal is to find the unknown vector X. Instead of the usual undergraduate method of doing the Gaussian elimination row by row, using so-called row equivalent operations, we will present these operations as a matrix multiplication. And the reason why we do this is because this perfectly fits more general iterative solution methods that are used in practice for very large matrices nowadays. So one of the row operations is row interchanges or permutation of rows. This is an introductory example. This is a m by n matrix A where we want to interchange the first and the second row. And we modify the identity matrix. So in the lower part, lower right corner, we have the identity matrix. But here in the first and second row, we switch the 1 from the 1, 1 entry in the first row to the 1, 2 entry. And we switch the identity matrix 2, 2 entry, which would be 1, to the 2, 1 entry. And it's very important now that you understand how matrices are multiplied together. So the resulting matrix, the first row comes from the first row of this first matrix. So when you multiply this with the matrix column by column by column, then this 0 multiplies the first row all the time. And then 1 multiplies the second row. Like the first row, first column, only A21 is getting picked up. Then the first row, second column, only A22 gets picked up. And that goes into the first row because we are using the first row for the multiplication. So the first row will be with the second row. And because we have the 1 here in the second row here, when we multiply this with this matrix, so the second row and the first column, only A11 gets picked up. Then this second row and the second column, A12 gets picked up. And then the last column multiplied with this row, then again the first A1n gets picked up. And then that means that we are picking up only the first row here, and because this is the second row that we are using, this first row goes into the second row. Make sure that you understand how this switching of these entries switches the first row with the second row. So this is one operation, and because the identity matrix is there, the rest of the rows do not change. The second type of row operation is when we add the multiple of one row to another row or other rows. In this example, we will add multiple of row 1 to row 2 and multiple of row 1 to row 3. So here we have the identity matrix that we start with. And now this is just a 3 by n matrix, only 3 rows. And this matrix in front is a 3 by 3 matrix. So 3 by 3 matrix times 3 by n matrix, the result is 3 by n matrix. So what you see here is that when you want to get the first row, you are using the first row in this matrix. And because it has only 1 here in the first entry, this picks up only the first row. So this row by this row by this row by this, only the first entries in the first row, they are the ones get picked up. And that means that they are staying there in the first row. In the second row, we get this from the multiplication with the second row, column by column. So alpha picks up the first row entries. For example, when you multiply this second row with the first column, we get alpha times A11 and then plus 1 times A21 and then 0 times A31. So alpha times A11 plus A21 goes into this second row. And then the same thing happens with all the other columns. For example, the last column, alpha times A1n plus A2n. Alpha times A1n plus A2n in this second row. And then the same thing with the, or not the same, but similar thing with the third row, that in this identity matrix we leave the diagonal entry, and by putting into this first entry the beta, now beta times the first row is added to the third row. One thing is that you should understand this multiplication, but then the other is that, of course, it's easier to do on paper to just say that you are adding alpha times row 1 to row 2, and you are adding beta times row 1 to row 3. You just have to edit column by column. So we're gonna, first of all, split up these matrices into more elementary matrices. I already mentioned that these are all coming from the identity matrix, modification of the identity matrix. So first of all, if you have IP as an identity matrix of size p times p, and then we have the standard basis vectors E1, EP in the p vectors of the scalars f, and then if you have an alpha scalar, then in general adding alpha times row I to row j, if I is different from j, what we need is the matrix E sub alpha, where you add to the identity matrix alpha times EI times EJ transpose. So the way this looks like, this additional part, is that alpha times, it's a scalar, and then the vector EI, it's a column vector. All these basis vectors are column vectors. So EI is a column vector where only the ith component is 1, the rest is 0. And then EJ, similar thing, but only the jth component is 1. But transpose means that instead of column, we have a row vector, where every entry is 0 except the jth one is 1. So how can you multiply together these two vectors, the column vector and the row vector? The column vector is of size p times 1. The row vector is a matrix of size 1 by p. So p times 1 times p, the result is a p times p matrix. And this p times p matrix, we have the property that it's 0 everywhere except the ith row and the jth columns intersection. And then this is what we are adding to get to the identity matrix. So in this case, this was alpha, but we also combine it together with another of this operation. So this is really just the identity matrix plus alpha added, alpha in the ij entry, because the matrix that we multiply alpha with is 0 everywhere except in one entry it's 1. The only reason why we are doing this, because it's kind of special structure, it's easier to see, and it's easier to see the properties of this special matrix then. So in general, if we have the ij entry fixed, the ith row and the jth column, then we can denote by Eij all these E alpha matrices of the form where this is the identity matrix plus alpha times EI times EJ transpose, where alpha goes through all the real numbers, or we could have any scalar actually. You could have complex ones also. So this is just the set with all these matrices. And the ij is fixed right now, so that's why we have the ij matrix. So what we can see is that this set is actually closed under multiplication, which means that E alpha times E beta will be E sub alpha plus beta. It's actually not so trivial, but it's possible to do this using the structure of the matrix. It's much easier to check this by just saying that E beta means you are adding b times row I to row j, and then E alpha means that you are adding alpha times the ith row to the jth row. So that means when you do this, do both of them, is the same thing that adding alpha plus b times the ith row to the jth row. This multiplication is also commutative. It doesn't matter, again, how you add multiples of a row to another row, in what order. But we could also try to check this from the definition of the matrices. It's just much easier to understand it using the idea that these are all just additions of one multiple of one row to another row. The identity matrix is also in this set, since if we use scalar 0, then we get that this is the identity matrix plus 0 times another matrix, which is just the identity matrix. Then these matrices are also invertible. The inverse of E alpha is just E minus alpha. And again, it's easier just to understand that to undo the operation of adding alpha times the ith row to the jth row is that you subtract alpha times the ith row, which means you add minus alpha times the ith row to the jth row. And that will undo the previous addition, so that means that you get back the identity operation. So these three properties actually means that this Eij set is a commutative group, because it has the identity and it has also inverse, and it's a commutative operation that we have with respect to the matrix multiplication. These properties actually also hold for more general matrices. Instead of these special basis vectors, Ei, Ej, we could have more general U, V, and W vectors, such that, for example, W transpose U is 0 and W transpose V is 0, which means also that they are orthogonal vectors. That would be the definition of orthogonality. So if you have this kind of vectors, then if you form this the identity matrix plus U times W transpose, note that this is not the same as W times U transpose, actually, so this will not be 0. This is actually a 0 scalar, but U times W transpose is a matrix, a P by P matrix. So if you take this and you multiply it with I plus VW transpose, then you get that this is I plus U plus V W transpose. And it's also the same as changing the order to have I plus VW transpose first, and then as a second factor I plus UW transpose. The proof of this is actually just writing it out. You have to be careful, you have to pay attention that matrix multiplication in general is not commutative. So if you multiply out the left-hand side, you get identity times identity, identity times VW transpose, and then UW transpose times the identity, and then we have UW transpose VW transpose. Then the first term is just the identity, the second is just VW transpose, the third is UW transpose, and here the multiplication is not commutative, but this is associative, so we can regroup. And if you look at the middle one, middle part, W transpose V is 0 by assumption, and then multiplying the zero matrix with vectors result in the zero matrix, so that part disappears. And the same would be if you change the order, of course. The next part is to look at permutation matrices. As I mentioned, this first operation was actually interchanging two rows. The other name for that is permutation, permuting the rows. So permutation matrices, in general, we can obtain an n by n permutation matrix by taking the identity matrix In and then interchanging some of the rows. And that means that P can be actually expressed in terms of the columns Ej, where j goes from 1 to n of In. Since the identity matrix has the columns of as columns the standard basis vectors Ej. So if you have this sigma one-to-one mapping, which is kind of permutation of the numbers, so sigma assigns numbers 1 through n to numbers 1 through n, basically permuting them, then you get a permutation. We can denote it by P sub sigma because it's coming from the sigma permutation as multiplication, adding up from 1 to n, the product of Ej times E sigma j transpose. So it's one of the column vectors, actually the column vectors are going from 1 to n through, and then it's multiplied with the transpose of some other column vectors. And which one, it depends on the special permutation that we have here. And then what you can see is that each of these products, Ej, E sigma j transpose, what it does is puts the sigma j throw into the j throw. And then what we end up is placing each row into some other row. And this permutation, the product of permutation, is not commutative, so we cannot talk about any kind of group or anything. Here is an example. N is 5, and then we have the permutations of 5 using this function, permutation function. So 1 becomes 4, 2 becomes 3, 3 becomes 1, 4 becomes 5, 5 becomes 2. It's 1 to 1, so there is no repetitions. Note. And then we have P sub sigma as E1 times E sigma 1 transpose, E2 times E sigma 2 transpose, E3 times E sigma 3 transpose, E4 times E sigma 4 transpose, plus E5 times E sigma 5 transpose. And then replacing the sigma values, sigmas with the values, we get E1, E4 transpose, E2, E3 transpose, E3, E1 transpose, E4, E5 transpose, E5, E2 transpose. And we already have these products before, so we saw what it means. What this means is that you get 1, 4 entry is 1, 2, 3 entry is 1, the 3, 1 entry will have 1, 4, 5 entry, there is a 1, and the 5, 2 entry, there is a 1. And then what you can see is that if you would change around the columns or the rows, that's the equivalent, then you could get back the identity matrix with 1s in the diagonal. But now what we have is a permutation matrix. Next definition is orthogonal matrices. If you have a n by n matrix V with real entries, we say that this is orthogonal matrix if V transpose V is the identity matrix. So actually what it means is that the column vectors are orthogonal because if you have the column vectors V1, Vn in this V matrix, then what this says is that the ith columns transpose, which means a row vector then, with the jth column is 0 if I is different from j and 1 if I equals to j, and this is actually the so-called Dirac delta. And that's how you get the identity matrix out of that. That this is only 1 when I equals to j, which means in the diagonal entries. Also note that permutation matrices are orthogonal. That's the reason we define these orthogonal matrices here, because it's interesting to see that when you multiply together the transpose of that with itself, you get the identity matrix. Next definition is upper echelon. A P by Q matrix U with k non-zero rows, as k is somewhere between 1 and p, is said to be an upper echelon matrix if the non-zero entries are in the first k rows and first non-zero entry in row I lies to the left of the first non-zero entry in row I plus 1, for I going from 1 to k minus 1, and then the remaining p minus k rows, if any, are all zeros. There's an alternative definition of this, and you might be more familiar actually maybe from undergraduate linear algebra class. It says first non-zero entry. This is sometimes called leading coefficient, the first non-zero entry from the left, and this is also known as pivot entry in the matrix. And instead of saying that as you go up from I plus 1 to ith row, this is to the left, the pivot. Usually actually we go from top to bottom, and then what we would have to say that in the row I plus 1, the pivot is to the right from the pivot in row I. So as we are going down, the pivots are moving to the right. And actually there is another name for that. This is also called the row echelon form in other books. So for example, here are two upper echelon matrices. What you see is that 5, 2, and 6 are the pivots, the leading non-zero entries in these rows. And as you go downward, they are moving to the right. Or if you want to use the first definition, as you go up, they are moving to the left. Here is another one, upper echelon form. As you go downward, the pivot first column and then in the second column, so we are moving to the right. And also the zero rows, if any, are at the bottom. So for example, these following two matrices are not in upper echelon form, or they are not upper echelon matrices. Let's see why this is not. So the problem is here that the second row is 0, and that's supposed to be at the bottom. But it's not at the bottom right now. The matrix D is not upper echelon matrix, and the reason for that is as you go from the first row to the second, the pivot, the leading non-zero entry, moves to the right, but then it doesn't move to the right again. Instead of that, it moves to the left. If you go from the second row to the third, now the pivot is to the left. But then that means that it shouldn't be upper echelon matrix. If it was upper echelon matrix, it should be moving to the right as you go downward. The pivot columns, so columns in an upper echelon matrix U that contain a pivot. For example, in this, the second and the third and the fourth columns are pivot columns because they have these leading entries, leading non-zero entries. That means the first non-zero entry in the row from the left. So column 2, 3, and 4. Then in this example, column 1 and 3 are pivots. The two pivot entries are -2 and 9. Column 1 and 3 are pivots. And then if you consider a linear system in the form AX equals B, our goal is to transform the system so that the left-hand side matrix is in upper echelon form, because from there it turns out that it's easily solvable. So we're going to use multiplication, as I mentioned, of the linear system in order to transform the A matrix into echelon form, upper echelon form. So U usually denotes upper echelon form. So let's say that G is invertible and U is already in upper echelon form with K pivots and with pivot columns U, I1, U, IK. Then the corresponding columns in A, which are A, I1, A, IK, these are also called pivot columns, although A is not in upper echelon form, but since somehow A is related to the upper echelon form U, we call those columns also pivot columns. And also the corresponding entries xi1, xik in the x vector will be called pivot variables. So we will be working with equation Ax equals b, and to solve this we want to apply the same row operation both on the left and on the right. So this is basic rule of solving equations, that whatever you do on one side you're supposed to do also on the same thing on the other side, so that you get an equivalent equation. That means that if you multiply A, the given left side, we also want to multiply B, which is the right side. So for this reason we put the two together, the A matrix and the B vector, into a larger matrix, and this is called the augmented matrix, and the notation is A tilde usually. So section 2 is about examples and some more details about the multiplication of solving linear systems. So first of all, let's consider linear system Ax equals b, with A given in this form and B given vector. Notice that the A matrix is already in upper echelon form. As you go with the pivots down, they are moving to the right. And the pivot columns 1, 2, and 3, that means the pivot variables are x1, x2, and x3. The rest of the variables, we only have one more variable, x4. We call this free variable. The other variable that are not pivot variables. So once we have an upper echelon form, we can solve this linear system from the bottom to the top. We write back the equation form of this matrix vector equation. So this says that 2x3 plus x4 equals 11, the right hand side, from the bottom row, the third row. And then we solve this for the pivot x3 in terms of the other variable. So we get 11 half minus 1 half x4. Then we continue upward to the second row and we substitute x3 because we already say that we solve this x3 in terms of x4. So the second row would be minus x2 minus 6x3 plus 13x4 equals minus 9. But as I said, we replace x3 with what we already have for x3. And then we multiply this out and we solve for x2, the other pivot variable. What we get is minus x2 equals 24 minus 16x4, or x2 is minus 24 plus 16x4. And then from the second row, and notice again that this is a pivot variable in terms of free variable x4, a non-pivot variable. Then we continue going upwards, so from the second row we go to the first row, and now we will have to substitute box x3 and x2. But first let's write out what the first row stands for. The first row stands for the equation 3x1 plus 4x2 minus x3 minus x4 equals minus 19. Then we replace x2 with its expression. We replace x3 with this formula, and then we only have x1 and x4 in this, so we solve x1, the pivot variable, in terms of x4, the free variable. Sometimes we write also that for the free variable, which is the non-pivot variable, we just write that x4 is x4. The reason why it might be useful to write this in this form, because then we collect the solution vector. So the solution vector x is supposed to have these components x1, x2, x3, x4, and then for x1 we write in the formula, x2 we write in the formula, x3 we write in the formula, and then sometimes students are stuck, what do we do with x4? Well, we just write x4 is x4. And then what you see is that the solution vector is written in terms of the x4 vector. There are also some constants. So it's very useful to separate this. Many times in the homework assignment it's required to separate, but it also has some very important theoretical uses, that you separate the constant vectors and then the x4 vectors, or the components with the x4 in them. So this is using the property of vector addition, that you add entry by entry the vectors. And then what we can do with this second vector, since each component contains x4, we can factor out x4 from the whole vector. Then still it might be confusing, how do we have x4 there? Then it's easier actually to say that instead of writing x4 arbitrary scalar, we just replace it with another arbitrary kind of scalar notation s. And we say that the general solution x is this vector plus s times another vector where s can be any scalar. So we also have infinitely many solutions, by the way, because s is arbitrary. So notice that here we have ax equals b equation above. So this had this form in a matrix vector form. A is a 3x4 matrix with 3 pivots. And then the system can be solved exactly the same way if you write any other b vector, any other b3 vector here. There is nothing special about b vector. So any other b vector would work the same to get a solution. That means if you consider this multiplication with ax as a transformation from the 4 vectors into the 3 vectors, so the linear transformation Ta x is just the matrix multiplication of A with x, matrix vector multiplication. This is a linear transformation, and what we have is that for any b vector we have a solution x using the same way of solving it. That means for any b vector in F3 there is an x such that Tax equals b, which means that actually the range of the transformation is the whole F3, because you can get a x that maps to b for any b in F3. So we have that the range is the whole F3 vector space. Notice also that we have a so-called solution set, where we write that the set as all possibilities of these additions for s scalars. And if you just use the notation u for the first vector and v for the second vector, that means that all solutions, or a family of the solutions x, can be written as u plus s times v, where u and v are these given vectors. Then notice that ax solution is just a times u plus sv, and since matrix multiplication has this distributive property, we can write this as a times u plus a times sv, and then this s scalar multiplication can be also brought outside. So we have a times u plus s times av vector equals to the b vector. And this holds for any s scalar. For example, it holds for s equals to 0, and it also holds for x equals to 1, because we get a solution whether you replace s equals to 0 or s equals to 1. But if you replace s with 0, then what this says is that a times u equals to b, and when you replace s with 1, what you get is a times u plus a times v is b. And from these two equations, what you get is actually that a times b equals to the 0 vector, which means that this vector v is in the null space of this A matrix. Because when you multiply it, you get the 0 vector. In fact, we will see later that the null space of the matrix is nothing else but the span of this vector, which means all the multiples of this given vector. Next example, consider the linear system Ax equals b with this A matrix, which is a 3 by 6 matrix, and b is a 3 vector. Note also that matrix A is again in an upper echelon form or a row echelon form, and it's even better because all the leading entries are 1. This is actually called reduced row echelon form. Used in many other textbooks because the pivots are 1. And this is useful to have pivots 1 because then we need a little bit less operation, we don't have to divide. The pivot columns are the first and the fourth and the fifth columns, and the pivot variables then are x1, x4 and x5. So we will solve the system for the pivot variables in terms of the other three variables that are x2, x3 and x6. So once we have this upper row echelon form, or just upper echelon form, again we solve the system from bottom to top. The third row stands for x5 minus 5x6 equals to 7. And this is easily solved for x5, 7 plus 5x6. Then we continue upward. The second row is x4 plus 5x5 equals minus 1. We already know what x5 is in terms of the free variable x6, so we plug this into it, and then we can solve x4 in terms of the x6 variable. Then we continue upward again to the first row, and now we have x1 minus 5x2 minus 5x3 plus 6x4 minus 2x5 minus 7x6 equals to 1. And then we substitute here x5 and also x4. And then in addition to the pivot variable x1, we also have x2, x3 and x6 that are free variables. So we solve x1, the pivot variable, in terms of the free variables. Once we have all the pivot variables in terms of the other variables, there should be no pivot variable on the right side anywhere. And you shouldn't solve for the free variables, only the pivot variables you should solve for. Anyway, the other variables can be written simply as x2 equals x2, x3 equals x3, and x6 equals x6, arbitrary. So of course, these don't say anything. That means really that these are arbitrary. There is no restriction on them. Then we collect the solution vector into a big 6 vector with the components. The pivot variables are replaced with their formula, and those are x1, x4 and x5. x1, x4 and x5, and then the other variables that are non-pivot variables are left as their own on their own. x2 is x2, x3, x3, x6 is x6. Then we separate the constants and the variables. So from constants we have 231 in the first component, 0 in the second, 0 in the third component, minus 36 in the fourth component, 7 in the fifth, and 0 in the sixth component. Then we also separate it by the variables. So you have 5x2, 1x2, 0x2 there, then 0x2 in the fourth component, fifth and sixth component, because there are no x2s. We separate also the x3s, 5x3, no x3, which means 0, 1x3, and then no x3, no x3, no x3, 0, 0, 0. Finally, the x6 variable, 167, 0, 0, minus 25, 5, and then 1x6. And then we factor out the variables. And we are left with 5, 1 for x2. Then factoring out x3, we get 5, 0, 1, 0, 0, 0. Factoring out x6, we get 167, 0, 0, minus 25, 5, and 1. And again, it's better to write it in parametric form so that these variables x2, x3, x6 don't confuse you. What it means is that the solution x can be written as this constant vector plus some, for example, r times the vector, s times another vector, and t times the third vector. And r, s, t are arbitrary scalars. So now what we have is that the range is the f6, the 6 component vectors, because again the idea is that since we have a solution, we can have a solution for any 3 vector, and this is actually a mistake. It should be 3 vectors. So the result is 3 vector when you multiply by the A matrix, because these are the B vectors. So we have one given B vector, but B could be anything. It doesn't change how you solve this. The solution changes, but the method we solve it doesn't change. So the range of A is the set of all 3 vectors, and the null space would be the linear combination of these 3 vectors. Now instead of one vector, like in the previous example, we now have 3 vectors. That means the null space is the span of these 3 vectors. Next example, let's consider this AX equals B system where A is this matrix with a bunch of ones. It's not a permutation matrix because we have several ones in each row, two ones in each row, and then some B right-hand side vector. The augmented matrix, we put together the A with the right-hand side matrix. Notice that this is not in echelon form because we have this 1 in the 4-1 entry. So we have to do something with this, and the way we get rid of this 1 is that we add -1 times row 1 to row 4, because then -1 cancels +1. That means what we want to do is we multiply E1 with the A matrix, or it's better to say that the augmented matrix A theta is multiplied from the left with E1, where E1 is this modification of the identity vector, where we put -1 here, which will add in the 4th row, in 4-1 entry. This will add -1 times row 1 to the 4th row. And then the E1 times A tilde is this matrix multiplication. It's better not to multiply this out, actually. It's better just to say that we are adding the -1 times row 1 to row 4, and it's easier to just do this, that you are adding -1 times row 1, which is the same as subtracting row 1 from row 4. So we get 0, -1, 0, 1, and -1. So don't try to multiply this out. Know how to create this E matrix, that's important. But actually to do it, it's better to do it just using the concept that this is adding -1 times row 1 to row 4. And what we get is still a matrix which is not in upper echelon form. The problem now, well, we have actually 2 problems. One is that the second row, from the second row to the 3rd row, the pivot goes to the left instead of to the right. So it would be better if the second row and the 3rd row would be interchanged, because then we would go from this pivot to that pivot. So we want to switch row 2 and row 3 for this reason. That's a permutation matrix. Let's denote it with P1. And switching row 2 with row 3 means that in this identity matrix, we switch around the 1 entries between the second and the third row. So originally the identity matrix has 1 here and here, but now we switch it from 2 to 3 and from 3 to 2. And that's applied to the previous matrix, which was E1 times tilde A, or A tilde. So P1, E1, A tilde is the E1, A tilde matrix with the second row and the third row interchanged. Again, you shouldn't start multiplying this. The way you should do it, just switching the rows. But you have to know how to write down this permutation matrix. So we get this, and still this is not in row echelon form. And now what we can do is we can add the second row to the fourth row to cancel this. So this is a bad entry because, again, the pivot is not moving to the right. This one is moving to the right, but this one is moving to the left. And then we can get rid of this by adding the second row to the third row. So adding the second row to the third row, second row to the fourth row means that the second entry in the fourth row must be changed to 1 in the identity matrix. And that will be the new E2 matrix that multiplies from the left this previous P1, E1, A tilde matrix. So this will add 1 times row 2 to row 4. This is how writing out the multiplication goes, that E2 is multiplying this previous matrix, P1, E1, A tilde. But again, actually, to do this multiplication we don't want to do, we just do row 2 plus row 3. And we get from there 0 in this entry, then 1 plus 0, 1, 0 plus 1, 1, minus 3 minus 1 is minus 4. So this is the new matrix. Still, it's not in echelon form because from the third row, so the pivots are moving to the right from the first to second, second to third, but from the third to fourth, it's not moving to the right, it's right under it. So we want to cancel this one by adding minus 1 times row 3 to row 4. So the addition is written as E3 multiplication with E3, where E3, the third added to fourth, so minus 1 times the third added to the fourth. In the fourth row we put, in the identity matrix, we put minus 1 in the third entry of the fourth row. And then with this E3 times this previous matrix, E2, P1, E1, A tilde, what we get is that the third row minus 1 times the third row added to the fourth row, or third row subtracted from the fourth row, we actually get 0 for the fourth row. And this is now in upper echelon form. The 0 row is at the bottom and the pivots are moving to the right as you go downward. So we solve then this upper echelon matrix vector equation. We write it back as Ux, where U is the upper echelon matrix without the augmentation. The augmentation is really the right hand side, so we put it on the right hand side. But the nice thing is now we did all these operations together for the left hand side matrix and the right hand side vector. So now we write it back in the matrix vector form, and then we solve this from the bottom to the top. The last row just says 0 equals 0, so we don't work with that. We just work with the non-zero row. This is x3. The third row is x3 plus x4 equals minus 4. We can solve this for x3 equals minus 4 minus x4. Also notice that x1, x2, x3 are the pivot variables, and x4 is the free variable. That's not pivot. So once we have x3, we go and substitute this into the second row's equation. The second row is x2 plus x3 equals minus 3. And we substitute x3 equals minus 4 minus x4. We solve this for x4. Then we go to the first row, which is x1 plus x2 equals 1. And we substitute here x2 equals 1 plus x4. And we solve this for x1 in terms of the free variable x4. Then we collect the solution vectors, or vector, the components x1, x2, x3, x4, written in terms of the x4 variable. Then we separate the constants. We have 0, 1, minus 4, 0, and the x4, minus x4, x4, minus x4, x4. Then we factor out the x4 to get minus 1, 1, minus 1, 1. And then it's customary to replace the free variable with a parameter s in order to avoid confusion. So the x solution is the 0, 1, minus 4, 0 vector plus s times the vector minus 1, 1, minus 1, 1, where s is an arbitrary scalar. So note that this x is actually the solution of this multiplied system, E3, E2, P1, E1, AX equals E3, E2, P1, E1, B, since that's how we got this U matrix and this modified right-hand side vector after all these multiplications. But all these matrices are actually invertible. So that means that if you start multiplying from the left with the inverses of these matrices, then actually all these cancel out and we get back the original system AX equals B. That shows that the solution of this upper echelon system is equivalent to the solution of the original system. It's important to check the solution not just because you can make mistakes while you do the calculations, but it's even important when you do this with computers or when people do this with computers. Then the problem can be that even if you follow the procedure, there might be some rounding errors. So depending on what kind of matrix you have, you can actually end up with an incorrect solution due to rounding errors, unfortunately. So to check the solution, you multiply out AX with this X solution vector. Well, I guess it's, in this case, X is better to write it in one vector format. Multiply this with the A matrix, and then you do the multiplication row by the vector, first row by the column vector, the second row by the column vector, and so on. And then you check that this is really the same as the right-hand side vector. Also note that sometimes you can avoid actually working with fractions. So there are no fractions in this example, but in one of the previous examples we got fractions. Many of the exercises will have integer answers. Of course, in real life, you never have integer answers with computers. Usually you get decimal numbers and truncated decimal numbers, rounded up decimal numbers due to the finite digit arithmetic of computers. So many of the homework will be solutions with integers. And for that reason, it's better to have ones in the pivots in order to avoid division. So let me start working out one more example without completely finishing it, just to explain this thing about the one in the pivots, if possible. So let's see this AX equals B linear system where A is this 4x4 matrix, B is a 4 vector. The augmented matrix, we put together the A matrix with the right-hand side vector into a bigger matrix. This is far from being upper echelon form. We have all these non-zero entries under the 1-1 entry. This shouldn't be there. So the brute force solution would be, or just following blindly the method would be to add 1/5 of row 1, because the 1/5 of 5 is 1, adding it to row 2, so that 1 cancels -1. But the problem is, if you start adding 1/5 of row 1, this is fine that you have 1 added to -1, but here you get -4/5, because the whole row 1 has to be multiplied by 1/5. So you would be adding -4/5 to 1, and then the result is what? The result is 1/5. So you immediately get fractions. This can be avoided by switching, for example, the first row with the second row. So that would be permutations. The first row switch with the second row. So we have the identity matrix modified so that we have this one and this one there. And then if you interchange the first row with the second row, that would be the permutation matrix multiplied by A tilde, then we get -1, 1, 3, 3, 2, and then 5, -4, 4, 4, 3 in the second row. And now look at what happens here. So we want to eliminate this 5 there. And what we have to do for that is 5 times row 1 plus row 2. That will be the new row 2. Then we also have to eliminate this 4. So this would be 4 times row 1 plus row 3. And then eliminate 3. That would be 3 times row 1 plus row 4. Because then you get -3 plus 3, 0. And in fact, you can do this in one step, writing after you have this permutation. Now the addition E1, E2, E3. So E1 is adding 5 times row 1 to row 2. Then 4 times row 1 to row 3. And that should be 3 here. So that's a mistake. 3 times row 1 to row 4. So this would be consecutive multiplications with these addition matrices, but the result is just the same as saying that you have 5 times row 1 added to row 2, so you have -5, 5, you have 5, -4 is 1, then 5 times 3, 15 plus 4, 19, again 15 plus 4, 19, and 5 times 2, 10, plus 3, 13. So that was 5 times the first row added to row 2. Then 4 times row 1 added to row 3. That's -4 added to 4, 0. 4 added to -3, 1. 4 times 3, 12, added to 7, 19. Again, 4 times 3, 12, added to 7, 19. And 4 times 2, 8, added to 5, 13. And then finally, 3 times the first row added to row 4. So -3 added to 3, 0. 3 times 1, 3 added to -3, 0. 3 times 3, 9 added to -9, 0. Again, 3 times 3, 9 added to -9, 0. And 3 times 2, 6 added to -6, 0. Then we have this new matrix. This is still not in upper echelon form because from row 2 to row 3 the pivot doesn't move to the right, and it should move to the right. So then the idea is that we want to eliminate this one using the previous pivot entry above it. That would mean adding row 2 times -1 to row 3, or with other words, subtracting from R3 row 2. So that means that we multiply this previous result with a new matrix E4, which is the identity matrix modified with this -1, so that this is the second row added to the third row. Second row because it's in the second column, and it's in the third row, so it's added to the third row. And then the multiplication of this E4 is just the same as saying that you subtract the second row from the third row, and you get, of course, 0 row there because it's the same. This is now in upper echelon form, so we can start solving it from the bottom to the top as we did before. Make sure that you understand these matrices, and also you know how to do this Gaussian elimination step by step.